Okay, it's now at 12:15. Our talk is supposed to start now. So welcome all to our next talk to be delivered by Amit Paka, who is the founder and the CPO of Fiddler AI. The topic is build high performance MLOps with ML monitoring and AI explainability. Uh, a little bit of bio about Amit. Uh, Amit is the co-founder and CPO of Fiddler, a machine learning monitoring company that empowers companies to efficiently monitor and troubleshoot ML models with explainable AI. Prior to founding Fiddler, Amit led the shopping app product team at Samsung and founded Parable, the creative photo network, now part of the Samsung family. He also led PayPal's consumer in-store mobile payments, launching innovations like hardware beacon payments, and has developed successful startups advertising, paid service, and pushing the envelope. He aims to leverage these skills to help define how AI can be fair, ethical, and responsible. So it's really great to have you with us today, Amit. But before we go to the talk, I want to remind all that we have our booths open. You are welcome to visit one of our booths to claim some prizes that are being offered there. And also, there's opening for those who are looking for employment. If you have any questions during the talk, just keep it in the chat box. I will relay that to Amit when he finishes his talk. So thank you all for coming. You now have our attention, Amit.
Sounds good. Well, thanks for the introduction, Franklin. So today, what I was going to focus on is really chatting about how do you in this world um, of machine learning operationalization, where models can fail silently, how do you build high performance, machine learning ops within your company? And where does monitoring fit in, and how does explainability fit in? So we'll kind of chat a little bit more about that. So I'll skip past my introduction since that was just given by Franklin, and let's deep dive. So a little bit about Fiddler. Our mission is to build trust with AI, and that's why the company was formed 3 years back. And what we offer is a solution called Model Performance Management that helps you ensure that the models that you're building, training, and deploying actually work at peak performance in this context of model decay and model failures. And it's powered by Explainable AI. I'll share a little bit more about the details around model performance management, but we'll deep dive into more how are the ways models can fail, and what are the ways you can ensure model performance is improved across model versions, and what role does explainable AI play in this within NPM. And feel free to ask any questions, like Franklin mentioned on the chat, and we'll kind of touch on that on the questions towards the end, maybe leave 5 minutes. So I'll talk for about 20-25 minutes, and we'll take questions at the end. Cool. So the focus of the conference is machine learning in production. And the reason that is the case is a lot of machine learning models historically have never left pilot stage, where a model gets built and it works well within the lab environment, but it's never productionized. And so from a statistic about 2 years back, 87% of those data science projects never make it into production. And why is that? There's 4 key reasons, and these are my reasons. One is that the models that get built, there is more of a focus on adopting newer technology rather than using technology to to really ensure you're making a business impact. So not tied to business impact is one of the key reasons it fails. It works well in a lab, but nobody wants to sponsor it into moving it into production. The second one is, when you build a model in a lab environment and it works well, how do you then ensure you're thinking about like the right steps in the workflow as you deploy. For example, you might have trained a great model, you might have curated data, trained a great model in your lab environment, but how do you make sure that that data pipeline is there so you keep on getting fresh data that's representative of reality? And so if you don't have a fresh source of data, you don't have a data pipeline, then it won't really matter that you've built this amazing model in like a pilot phase. Thirdly, machine learning is very different as compared to traditional software, and we'll talk more about that and why it needs a more custom approach to monitoring. And because it's not the same as kind of traditional software, you like really going on to the fourth point, you cannot use traditional software processes to actually deploy it. You need something special, and that's really MLOps. How do you ensure that you have this kind of pipeline that brings in data, trains models, ensures that the model is validated, checks if the performance is well in the context of an existing model, if there is an existing model, you, like really checks for bias if that is one of the focuses of the use case. Check whether the model is actually performing better in production environment as compared to an existing model, and see how it is different, and then ensure that when it's deployed, it's not failing, and if it is, feeding that back into the system. So the lack of this process is also one of the key reasons why existing data science projects fail. And so we'll talk more about we'll first talk about monitoring aspect of MLOps, right? There's the part of MLOps that's labeling and training and deployment. We'll make a business case for monitoring these models. The first point to consider is that machine learning, when teams are adopting machine learning, they actually build a data science team, and this is a significant data science team. And so it's expensive when you want to adopt machine learning. And because it is expensive, machine learning gets applied to a lot of the use cases where you get the highest ROI. Like, for example, if you're in like a social media company, you might apply it to like your feeds, your like main social media feed, which is one of the key ROIs of your company. If you're like a fintech company, you might apply it to really solve for fraud, which could reduce a lot of your costs. And so it's applied to a lot of high ROI use cases. And thirdly, models can fail silently. You won't even know when they fail. And even if they don't fail, the reality and the data might change, and the model's predictive power can go down. And so because of all these three reasons, it's expensive, you apply it to high value use cases, and they might fail and not deliver on those use cases. So you're losing money if you don't monitor ML. And so really, that's the simplest business case for trying to monitor your machine learning models. Let's deep dive into operational risks. What are these operational risks that your model run into? You've trained a model, you're looking to deploy it, you've deployed it. What can go wrong, and what do you need to ensure that you're looking out for? So models can fail for a variety of ways, and they fail frequently. It's just that you don't know that they're failing. The first reason, of course, is that a model's performance can vary over time because the models have been trained on a certain fixed set of data, and the data itself can change, or like the concept can change. For example, spam filters, the way they catch spam, the actual definition of spam can change over time. So you need to ensure that you have a way to catch performance degradations of the model. At times, so a lot of performance is tied to how the data is going into the model and what the model was trained on. And so if there is a shift in the data that the model is seeing in production versus what you've trained the model with, then that is going to impact performance, and you want to make sure that you have a handle on that. And data going into the model as it's making inferences, that might not be something that the model recognizes. So the model might not make a correct decision. So the integrity of the data going in should match the integrity of the data that you train the model with. And many times, given changes in the data pipeline, this might not be the case. So the model might make slightly incorrect decisions that you won't even catch until much later. And of course, if your model has got bias implications, you want to ensure that models which, like, as you train a model or as you select data for a model, and as the model gets operationalized, you want to make sure that you can assess for bias and you can mitigate for bias, because models can add or like they can add or they can amplify bias. And when models even make decisions, it's very hard to know why the models are making decisions. Of course, machine learning models are constantly becoming a black box. Teams are going increasingly to more kind of complex models. So how do you bring that level of transparency into a team so that you can not only gain trust, but also you can make it easy to debug? Let's talk a little bit more about this last point in detail. And so because models are increasingly becoming complex, they're no longer logistic regressions, no longer decision trees, they are becoming like complex random forests or deep learning models. And that makes it much harder to understand why they're making decisions, and you don't have visibility into model performance. You don't know if there's potential bias or drift, given how hard it can be to reverse engineer a model, and there's no explanation of why a model makes a decision. And this is not just a data scientist problem. It's a problem that impacts a lot of stakeholders, all the stakeholders of the model, from the internal stakeholders to the external stakeholders, including auditors and regulators. And so this is one of the key differences that machine learning is facing in the context of traditional software. And there are also existing regulations and guidelines that need to be complied with, even when you deploy machine learning models for use cases, right? For example, if you have a lending model, then the existing lending laws, Equal Credit Opportunity Act, and so on apply to you. You also have SR 11.7, which kind of came out as a result of the financial crisis. And then, like lately, there have been more proposed regulation that's customized towards AI itself. A lot of all the historical regulation was tied more to, let's say SR 11.7 was tied more to quant models, but now the new regulation is more custom to AI, and so they want to ensure that there is trust in AI. And I have this quote from Margaret on the recent proposal for AI regulation that kind of came out of EU. Their focus with the proposal is to bring trust into AI. So it's not a nice to have anymore; it's a must. And they mandate explainability and monitoring for high risk AI systems. And if you don't abide by these kind of regulations, you could still run into PR issues. And these are just a few of the news articles recently of teams running afoul and really not staying on top of the inadvertent impact that models can have. So what is the solution? And let me introduce model performance management. And so historically, in the DevOps context, there was a notion of APM, application performance management. And so you have the likes of Datadog and the likes of AppD, the likes of CloudWatch, that help DevOps teams really understand how application performance is doing, whether it's at the actual infrastructure level or at the app level. For machine learning ops, that is equivalent. We call it MPM, model performance management. Let's deep dive what it means in the context of MLOps, right? So the broader analogy is APM is to DevOps what MPM is to MLOps. And so why do you need MPM, model performance management? So within ML, the workflow is really iterative, which is different from like traditional software. You don't just build one model. you build multiple versions of the model, and when you deploy a model, the model can lose its predictive power as data changes. Then you train another model, and you do this iteratively. So this is a very unique dynamic of machine learning models. And there are a lot of steps in this workflow, and models can change through these steps. So you need visibility across all the steps of the machine learning, workflow. In this case, there's training and validation, and these are offline steps. So you'll see this offline. So this happens offline. And when you validate and have a trained model, you actually deploy it. So this is when the model goes online. And so you deploy the model, you monitor the model making predictions, and then you analyze the model if the model is having real-time issues, and then you feed that back into training. So because of the black box effect that a model can have, given its opaqueness, in order to do iterative workflows and keep on improving performance, you need to understand the model behavior. And so the way NPM fits in is it's a process where you plug in to all the aspects of the ML lifecycle. And in the actual training step, you log training and test data sets, and you can check for bias and see if the features are of good like quality. Then in the validations step, you can ingest the model. You can compare a previous model to an existing model. You can see a slice of data and see how's the model doing on, let's say, loans made in the state in like the state of Washington, or like fraud coming out from a certain country, and then see if the model how the model is doing, if the model is doing bad in that slice, and what you can do about it, and really compare that across models if you have a new model coming in. Then once you're confident that you validated, you deploy a model, and that's when you record traffic and data. And like typically you might have an existing model and you have a new one, and you actually compare them, side by side on how they're doing, maybe in a shadow mode, or maybe using canary traffic. And then you monitor the models itself once you've made a selection of which model you want to like really deploy at scale. You see how the performance is shifting and drift and outliers, and we'll go into deep dive into this like next. And then you can then set alerts on conditions that might happen. For example, you might say, hey, I really care about like loans made in the state of California because that's one of my highest serving market. And so in case accuracy goes down or there's drift over there, let me know. And so then that when that triggers, then you go into analyze and see, why is that happening? Is there something changed in the business? And then you feed that back. If there is something that's changed in the data, you actually create use these insights to create a new data set and actually feed that back, and then build a new model. So this iterative workflow, as you build newer versions of the model, as the model's performance is deviating, and as you're building new models to actually bring the performance back. So this whole workflow feeds into NPM, and NPM is really at the heart of your ML workflow. It's not replacing your training step. It's not replacing your actual deployment kind of systems. It just sits in the center and records everything to ensure the models, as they're being iterated on, works in high performance. Let's talk a little bit about how to catch operational issues. So the first one is, if you have labels coming in, right? Your model is making predictions. You have labels coming in. This is typically not the case that you have real-time labels. You may or may not have labels. And if you do have labels, they might be lagging labels, right? In case it's real-time, it might be something like an add-to-cart model or an ad display. But if it's lagging, labels, you might have something like credit decisioning. And so using the labels, you can plot how your model is doing over real time, over time, and you can kind of get a sense of how's the accuracy drifting, and then maybe use that to trigger if your model needs to be retrained. And if you, at times, you don't have labels, and so you're trying to use a leading indicator of when your model's performance might be like changing. And typically a model was trained on some data, and that's the data that it can best make predictions on. And so when the data changes, the model's predictive power can shift. And so really drift detection is really trying to assess, you've trained the model on a certain distribution of data, and the model is seeing a certain distribution of data when it's deployed. If that's very different, then the model's performance will change. And so in this case, the dark blue line, you can see it spike towards the end. That's the drift. And so when that happens, you want to investigate. So in this case, there's kind of multiple ways in which you can calculate this drift itself. You can use PSI, which is typically used in like financial services. You can use scale divergence and so on to actually calculate, to really quantify how much is this drift, so that you know when you want to act on it and investigate. And finally, looking at like a lot of data going into the model comes through data pipelines, and there might be shifts in the data pipeline, or there might be changes in like data versions. And so your model might be seeing data that might be incorrect, and so it'll just fail silently. And so you can catch these issues at model inference time, and you can catch issues like if like a value is missing, or if there's a range mismatch, right? For example, you might have only four types of like four like types of products in market, and maybe your model sees a fifth type, and it'll just make a prediction and not really know if it's a right prediction. So it's a range mismatch. Or schema mismatches. You have schema mismatches all the time. So you need to catch all these data issues, because over time they might reduce the predictive power of your model. And even if you've assessed your model for bias, as the data changes in live, in a live setting, your model might change, and data shifts might introduce operational bias. And so you want to make sure that you're monitoring how are some of these bias metrics doing in real time. And then, if you have an alert, you can jump on it and see if your model needs to be retrained, or if there's some kind of representation issue that you need to address. And so in this case, you could have metrics like, in this case, you could have disparate impact that you're monitoring. You could have demographic parity and so on. You could also monitor simple metrics like TPR, true negative rate, and so on. Now, in the context of NPM, you're looking at this iterative workflow of like machine learning. So how do you build and iterate and improve the model performance? So when you're doing champion challenger like kind of monitoring, you have a champion model that's running in production. Now you've trained a challenger model. So post-training, what you want to do is you want to compare these models and see how are they differing. Right. In this case, what you're seeing is you are running analysis on a champion model, which is version 2. It's now running in. It's now trained, and you want to compare that to your So you got version 2, which is a challenger model, and the champion model is version 1. So now you want to compare your actual challenger to your champion, and what you're seeing is feature impact. And you're seeing the dark blue one is what are the features that are important to your challenger model, and what are the features important to your champion model. So how is your model changing in terms of how it's absorbing like the features itself? So you could start to do this at the global level, at the model level, and then you can drill down into slices, right? In this case, like let's say you want to see how it's doing in the context of loans made in California. What is the feature importance there? Right, so you can kind of see how is the performance changing in like post training of champion versus challenger at the global level or at the slice level. And post deployment, you want to run these side by side, and it could be using shadow traffic, it could be using canary traffic, it could also be using post replay mode. And so you have the champion output. So you have a model making predictions. It's your champion model. You can run the same predictions, the same input through to your challenger model, and then compare it side by side and see how's the first model, shifting as compared to the second model. Where is the performance of the first model changing or remaining the same as compared to the second model? And when there is a difference, you actually deep dive and then you analyze that in real time. And typically, even when you actually monitor a single model, you may want to look at a certain segment of the data to actually deep dive into it. And so in this case, I'm trying to monitor employee departures from a company. And so I want to see like how are employees departing from each of the department itself. And so that's where I want to monitor how the model is doing in a specific segment. And so that gives you deeper insights on how's the model doing in that segment versus the rest of the model or across segments. And so this helps you really understand not just at the global level, but within a segment of interest, how your model is doing, and really gives you deeper insight. So you can actually better differentiate what parts of data you may need to augment if the model needs retraining for you to kind of better improve the performance of this model in that segment. Cool. I'll quickly run through explaining and root causing, and then we'll pause for a few questions. So where does explainability fit in, right? Typically, so explainability is a way to really understand why is the model making a decision, why is the model's behavior working in a certain way. And so you can explain it at the prediction level, where you say, how does each input impact? You can explain it at the segment level, like explaining loans from, let's say, California. Or you could explain at the global level, explaining all loans. And you can get an understanding of why is the model making that specific loan decision, all these loans in California decision, and all the loans globally decision. And you can explain a prediction. When you explain a prediction, it's really telling you which of the inputs, in this case, let's say debt to income, is contributing how much, in this case, 20%, to the output itself. In this case, it's high risk of 0.235. And so there's multiple techniques to be able to use this and kind of figure this out. And the same thing works even if you have an unstructured text model where your model is predicting, that that the sentiment in this is a positive sentiment, and which are the words that are contributing to it. So you can explain that prediction and attribute it to each of the words. Explanations have recently gotten a thumbs up from the Fed itself. I just wanted to put up a comment from the Fed Reserve Governor that explanations are going to be one of the key ways into helping all the stakeholders of financial services models to really understand how the model is working. And when you explain a segment or model, like, you get different kinds of explanations. You get feature impacts. You can get PDPs and so on. So you can explain it globally or locally. And finally, putting it all together, monitoring as you're monitoring. So here, what you're seeing is you're actually monitoring for drift. And so when you see the drift increase, you can actually drill down, and using explainability, you can figure out what is causing the drift. In this case, one of the inputs, number of products, had a very high drift and a very high impact. And then you can drill down and you can see what is causing the drift using explainability. So this is just a high level, use case where trying to put in visibility and explainability to help root cause not just what is happening, but also why it's happening. So I'll stop there. That's in a broader, that's the broad kind of explanation of how you deploy machine learning MPM to include monitoring and explainability and this whole iterative process that is machine learning. Let's see if you have any questions.
Thank you so much, Amit. But thank you for the nice, wonderful talk. It was very engaging for making our time. So now I want to take some of the questions from the audience. I will start with Gian Mario. He has lots of questions. So I'll start with the first one. It says, if the ML system has a feature store, data validation should happen there and not at serving time. I don't know if you
Yeah.
something.
So I think data validation can happen.
You can go ahead.
Data validation can happen at multiple steps, and there's actually multiple tools. There's also data validation tools itself. But it helps if you can get the context of how it's impacting the machine learning model itself. And so many times, a lot of the data. Sorry, it feels like my voice is echoing. So I was just saying, many times the data issues still show up at serving time, and when they do happen, really trying to find out what is the impact in the context of the model, that helps for you to figure out if it is something that you should be looking at, right? For example, if it is a feature that has minimal impact to the model, you may want to maybe queue up the fix for that in a few weeks versus doing it right away, right? So there are still errors that might happen downstream at model serving time, and the context of the model helps at the time that the errors are happening for you to figure out and really triage if it is something that you should be looking at.
Okay, thank you. I hope your question is answered, Gia Mario. The next question is, what's your experience and tips for explainability for text? Those techniques don't seem to be as mature as sharp and similar for numerical or categorical attributes. So
the explainability techniques for unstructured data are like the likes of integrated gradients, right? The likes of GradCam versus SHAP. Personally, they are more faithful to the model than Shapley values is. So I think they just need a lot of broader awareness creation that the explanations there mirror the model more closely than Shapley, where you could actually lose some of the granularity as you're trying to figure out the values itself. So we've had pretty good experience using integrated gradients for explainability of text, and we think, and really not to mention that they are much faster, right? Calculating gradients is much faster for a model with large text than doing Shapley values on that, which could take much longer. So it's more faithful and it's faster.
Okay. Thank you so much. If you have any more questions, you can add to the chat. Well, while we wait for the questions, I want to know if you can share your email in case someone wants to reach you later. Okay, any other participants want to reach across to you later? So
yes, that's a good point. Yeah, my email is amit@fiddler.ai. I can type it in chat as well. Feel free to send me a note if you have any questions. Happy to answer. This machine learning ops, as we all know, is still evolving and will continue evolving. And I think now the processes are starting to form, and I'd love to hear how teams are tackling the notion of monitoring and how and trying to really ensure model performance is being maintained across versions, and the risk of introducing a new model is being contained by really validating and understanding how the new model differs from the existing model. Yeah, I'd love to hear from folks if you have any questions and if you'd love to share your experiences.
Okay, thank you so much.
Thanks, everyone.
Thanks for the email. Okay, I'm not sure we have any other question to ask. In the absence of any other questions, so I want to thank all for attending. Thank you, Amit, and hopefully we'll get to reach out across to you on through email or maybe LinkedIn. Okay.
Cool. Sounds good. Thanks, everyone.